Hello everyone, welcome to my YouTube channel. So today we are going to discuss about the anemia. So let us begin with the definition. So anemia, as the World Health Organization define as decrease in the hemoglobin. Like first and foremost, decrease in the hemoglobin concentration. So a specific cutoff point which varies by age, sex, physiological status to account for population differences and specific conditions like pregnancy. Okay, so which means decrease in the hemoglobin levels in the non-pregnant women as well as in men, so which is below or lower than the 12 grams per dl and 13 grams per dl in men, so it is considered as anemia. If it is more than this, so it is considered as normal. So grossly, it is classified into two mainly. One is based on the cause, another one is based on the morphology. Okay, so it could be overlapping one and each other based on the cause as well as the morphology. We'll see like which cause may cause which morphological condition or type of anemia. So under cause, we have first one iron deficiency anemia, and then megaloblastic anemia, hemolytic anemia, aplastic anemia, sickle cell anemia, thalassemia, anemia due to chronic diseases, and pernicious anemia. In detail, we are going to discuss all about these in further videos. And secondly, based on the morphology, it is classified as microcytic anemia, normocytic anemia, as well as macrocytic anemia. Okay, there is a correction here, macrocytic anemia. So irrespective of all the morphology and causes, all types of anemia has three classical symptoms. You can see here fatigue or weakness, dyspnea, that is shortness of breath or difficulty in breathing, and also we have pallor. Okay, you can see here in the GIF, just I have demonstrated here like how it looks, weakness. So all day we'll be feeling tiredness or weakness, and we don't have any energy for performing any activity, as well as this is dyspnea, shortness of breath or difficulty in breathing. And we have pallor. You can see here in this diagram there is a paleness in this hand, whereas compared to this normal hand, this is normal and this is anemic hand. In further to in pathophysiology, we'll discuss like how, why there is dyspnea, why there will be fatigue. Okay, so firstly, we'll take microcytic anemia based on the morphology, and iron deficiency is the cause for microcytic anemia. So further, another few more causes for microcytic anemia. As I said, iron deficiency anemia, thalassemia, and anemia due to chronic diseases, and sideroblastic anemia. So these things you can remember with the mnemonic Sita. So goddess Sita. So S refers to the sideroblastic anemia, I for iron deficiency, and T for thalassemia, and A for anemia due to chronic diseases. Okay. So what might be the cause for iron deficiency? We need to understand here, like that is chronic blood loss due to GI bleeding might be there, or menorrhagia, or poor dietary intake. We are going to discuss about this, like what is the dietary intake, how it get absorbed in the pathophysiology. And increased demand and decreased supply. There is imbalance between increased demand and decreased supply. So in that condition also there will be iron deficiency. Example, pregnancy and growth, okay, during puberty. And also we have malabsorption if there is an any pathological condition in the GI. Okay, so there, because GI is the place where iron get absorbed. So if the person is suffering with the celiac diseases, that is GI disturbances, then there is no absorption of iron, which causes the iron deficiency in the body. And gastrectomy, so if any removal of any part of the GI tract, so that also leads in the iron deficiency. Further to the causes, we have thalassemia. It is a genetic defect in which the globulin chain production will not be occurring, that is beta thalassemia and alpha thalassemia. We'll discuss in pathophysiology. There are four components in the hemoglobin, which is 2 beta and 2 alpha. So how it is located, we'll see in the diagrams. Next, we have anemia due to chronic diseases. So presence of chronic diseases like CKD, okay, CKD which causes and liver diseases. So liver will secrete this protein, that is hepcidin. The functions we are going to see in the pathophysiology. And also CKD, erythropoietin, there is a protein which will be released from the kidney, erythropoietin. Okay, this is the protein which will be released from kidney, which helps in the synthesis of RBC. Synthesis of RBC. So disorders of liver as well as kidney, so that leads to decrease in the proteins which are required for the absorption as well as uh, the function of RBC. Fourth one, we have sideroblastic anemia. So this is defect in the heme production, heme production or heme synthesis. So this iron will not be trapped in the heme. Okay, that structure is there, so it will not be present in that, and it will be available freely. So that leads to the uh, destruction of RBCs as well as. Okay, so sideroblastic causes for sideroblastic anemia is congenital, that is from parents to children. So which is very rare, but acquired is the most important cause which can cause sideroblastic anemia, which may result in to microcytic anemia. So examples like alcohol, we have lead poisoning, isoniazid, chloramphenicol, and myelodysplastic syndrome and copper deficiency. Okay, so here this iron isoniazid, this is an anti-tubercular drug which can cause sideroblastic anemia as well as iron deficiency anemia. So under pathophysiology, I have drawn the diagram which can explain about the absorption of iron as well as conversion of iron inactive form to active form, and how it goes to inside the tissue, and it reaches the circulation. From circulation, how it goes to the bone marrow, we'll discuss here. Okay, so as we take iron in the form of food, so that is present in the form of Fe3, that is ferric. Okay, ferric form of iron which is inactive in nature. So it is inactive in nature. So it has to get activate in order to get absorbed in the tissue. Okay, here. So to get convert HCl from the stomach helps in the conversion of inactive form of iron, that is ferric, to ferrous, that is the active form of iron. Correct. So here inactive form to it has got converted into active form. So now this ferrous form of iron, it is ready to get influx. Okay, so this is the lumen of the GI tract. I have taken this part. Okay, here there will be tissues and blood circulation. So from here, this is the lumen, and I have taken this tissue. This red color tissue is I have drawn here. So this is the red color tissue. Okay, so this GI tissue has enzymes or receptors. Two receptors are helpful in absorption of iron. So this is Fe2 plus. Okay, so first receptor, that is DMT, that is divalent metalloprotein, which helps iron to get absorbed. Later, there is another protein called as an ferroprotein, which convert Fe2 to Fe3. Okay, so it should be active only in the tissues, not anywhere in the extracellular matrix. It will be in the inactive form only. So in the cellular level, it is active. Okay, so Fe2 will be active in the cellular level. Extracellular level, it will be present in the form of Fe3 plus. So who is converting here? Here in this diagram, you can see ferroprotein is the protein which converts the ferric to ferrous. So here this is the blood. This is the lumen of GI tract. This is the GI tract tissue, and next here we have the circulation. Okay, so this is the blood circulation. So now our iron has trapped, or it has come to blood circulation. And one more thing has to be remembered here. There is liver, so which will be present here, if you see, if you look at anatomically, so this liver will be producing one protein called hepcidin. I have written here hepcidin. What is the function of hepcidin? Is one is to conversion of uh, along with ferroprotein hepcidin, which will convert Fe2 plus to Fe3, as well as it will inhibit the ferroprotein. This protein is there, no, which was converting Fe2 plus to Fe3 plus. So this hepcidin will inhibit ferroprotein. Why inhibition of ferroprotein is required? So question is that, so that is required because if there is an excess iron, Fe3 plus is trapped in the blood circulation. If there is an excess or increased level of iron, then there is requirement of inhibition of this protein in order to reduce the extra conversion of Fe3 plus in the blood circulation. Okay, so this is one use, and also it will helps in the hepcidin helps in the storage of Fe3 plus in the liver. If there is an emergency requirement of iron, then it will be released in the circulation. Okay, so this is about the absorption as well as the conversion of iron. Okay, next you can see in the diagram, so further to same thing. Okay, here is the lumen, and this is the tissue, and here is the circulation, blood circulation. Okay, so we had taken food, iron from the food, so which will be available as heme iron as well as non-heme iron. So ultimately Fe3 will get convert into Fe2, right? We had seen in the diagram as well. So this Fe2 plus will be getting influxed with DMT, that is divalent metalloprotein transferrin. Okay, so this has entered, so mucosal ferritin. So from the tissue, this Fe2, that is ferrous, will be coming into the circulation. As we have discussed, there is requirement of conversion from Fe2 to Fe3 by ferroprotein. Okay, ferroprotein will helps in the efflux of iron as well as conversion of Fe2 to Fe3. Okay, here we have hepcidin from the liver. Okay, so which will inhibit the ferroprotein in order to prevent the excess availability of iron in the circulation, right? So this ferroprotein is inhibited by hepcidin. Also we have here hepastin, so which helps in the control of this ferroprotein receptor. Okay, so here Fe3 has came into the circulation, so it goes to the blood circulation. From there it goes to, from the circulation it goes to the target areas. Okay, so further to target areas, where it goes, like it goes to the bone, it goes to the muscles, and it goes to the other tissues wherever the function is required. Okay, other tissue. So in anemia, what is the role of iron? We had seen the absorption from food to from and conversion in the tissue level as well as conversion in the blood level. Okay, so after conversion it has to go to the target areas. Let's suppose it has reached target areas. One is bone. Okay, so we are discussing anemia, so I'll concentrate only on the production or synthesis of RBCs, like what is the role of iron in that. So you can see here in the circulation we have RBCs. So right, RBCs are there in the blood vessel. If you take each RBC, like how these hemoglobin are located in the RBC, as shown in the picture, you can see here it is located as 4 molecules. Okay, if you remember, there is about the chain, like here we had discussed, this is the cause, thalassemia, globulin, so defect in the globulin. So these are the globulins, 4 globulins. Okay, this is, let's suppose, beta 1 globulin, and this is beta 2 globulin, this is alpha 1 globulin and alpha 2 globulin. Okay, so as we discussed earlier, so there are 4 globulins, that is heme globulins, are present in one hemoglobin. So if you take one hemoglobin structure, there are four parts of the globulin heme groups. Okay, so that is beta 1 chain, alpha 1 chain, and beta 2 and alpha 2. Okay, so these chains are there, four chains. Each chain contains one molecule of heme group as well as iron. Okay, so you can see here this red color is iron. Okay, so this iron will be holding one molecule of oxygen. Okay, this is the structure of hemoglobin. Each hemoglobin has four globulins, that is alpha 1 and alpha 2, beta 1 and beta 2, four globulin, and each globulin will be having one heme group. Along with one heme group, there is an iron, one iron molecule will be there, and it will be attached with one oxygen molecule. Okay, so this oxygen will be delivered to all the tissues in order to further respiration. Okay, so this oxygen will be got exchanged with the carbon dioxide. So I think we have discussed oxygen will be replaced, oxygen will give to tissue, and from tissue carbon dioxide will be taken up, and that will be expired. Expel of carbon dioxide occurs as in the result of expiration. Okay, inspiration and expiration. Inspiration is oxygen, intake of oxygen, and expiration is expelling the carbon dioxide. Okay, so gas exchange occurs in these areas, these globulins. Okay, so you can see here the sky blue color is oxygen, and below to that red color is iron, and here is the heme group. So this is how the structure of hemoglobin is structured, so which has heme group as well as iron as well as the oxygen. What happens if iron deficiency? Also you can see here for structure of iron and heme. So what happens if iron deficiency? Okay, reduction level of iron is there in the body, so there is no iron here. So if there is no iron, means there is no combination or compilation or binding of heme group as well as the oxygen to the iron. So if there is no binding of heme group as well as oxygen level, oxygen molecules with iron, so ultimately there will be decrease in the heme group as well as oxygen level. Okay, so which causes the hypoxic condition, also breathing difficulty. So we had seen in the classical symptoms of anemia, so dyspnea, that is breathing difficulty. You understood why there is deficiency, dyspnea, that is because of decreased oxygen level. Why? There is no iron to bind with oxygen. Okay, ultimately there will be decrease in the oxygen. If tissues are not doing any activity, respiratory activities, like there is no oxygen is required for the generation of ATP. So we will discuss in some other classes. Like as of now, you remember oxygen is required for the generation of ATP. If there is no oxygen, reduction in the oxygen in the tissue level, there is no generation of ATP. If there is no ATP, the person will feel weakness. Okay, this is how they are located. And why pallor? Why there is decrease in the red colorness? That is because of loss of attachment of heme group with the iron, because there is iron deficiency in our body. So there is no iron to bind with oxygen as well as heme group, hence there is pallorness we say. So heme, which is the molecule which give redness, red color to the blood, right? Where were we were here. Okay, so here, right? So decrease in the iron, which causes uh, detachment of heme group as well as oxygen. So hence we see pallor as well as hypoxia, that is shortness of breath, dyspnea. Okay, so to want to see how a microcytic anemia looks like, this is normocytic, which has the diameter of 80 to 100 femtoliters, and microcytic when it is called if the diameter of the RBC decreased or lesser than the 80 femtoliters, 80 femtoliters, so it is considered as microcytic. And macrocytic if the diameter of RBC is more than 100 femtoliters, then it is called as an macrocytic. Okay, so pathophysiology and the causes for macrocytic anemia will be seeing in the next video. So yes, this is about iron deficiency anemia or microcytic anemia.